Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. A contribution to mathematics that is groundbreaking is always front page story in mathematics publications. In the world of mathematics, it is a tradition to invite a research mathematician that contributed to mathematical knowledge and to invite him or her to deliver a research lecture on his or her contributions to mathematical knowledge and to deliver that research lecture to the forthcoming International Congress of Research Mathematicians. That International Congress of Research Mathematicians is held once every 4 years. My mathematical invention of how to solve the toughest mathematical problems that arose in physics, calculus, and algebra, and how to solve those mathematical problems across my ensemble of 64 binary thousand tightly coupled processors occurred on the 4th of July 1989 and occurred in Los Alamos, New Mexico, United States. 2 years later, and on July 8, 1991, in Washington, in the District of Columbia, United States, I gave an esoteric research lecture that was for research mathematicians only. 9 years earlier, the same lecture in Washington, District of Columbia, attracted only one attendee. But on July 8, 1991, I was still getting cover stories, including a cover story on that day's issue of the Detroit Free Press and a PBS Public Broadcasting Service television interview the following day in Cambridge, Massachusetts. For the media attention my contributions to algebra and calculus were getting, I was not surprised that my 11 a.m. lecture in the Dover Room of the Washington Sheraton Hotel in Woodley Park was so well attended that all the seats were taken. In fact, research mathematicians were violating the fire code by standing on restricted spaces. That research mathematics lecture on my contributions to algebra and to calculus was preceded by a cover story in the May 1990 issue of Siam News. The Siam News is the top publication in mathematics. The Siam News is written by research mathematicians and written for research mathematicians. Siam is the acronym for the Society for Industrial and Applied Mathematics. At that mathematical congress of July 8, 1991, I was the research mathematician that was in the news the most. I lectured to a standing room only audience of research mathematicians. I lectured on how I mathematically invented how to solve the toughest problems arising in algebra, calculus, and physics. I lectured on my new massively parallel processing way of solving the toughest mathematical problems arising in extreme scale computational physics and solving those problems by massively parallel processing 64 binary thousand algebra, calculus, and physics problems and parallel processing them at once instead of the old way of sequentially processing only one mathematical problem at a time. My mathematical processes were called executing a set of floating point arithmetical operations that solves a linear system of equations of algebra that in turn approximates a system of equations of calculus. I invented new algebra and new calculus. As a research computational mathematician that came of age in the 1970s and 80s, I was searching for new algebra and new calculus and searching for new mathematical knowledge and searching for that knowledge alone. I was searching alone, not by choice. I did my research alone because I was scorned, ridiculed, and rejected by the research mathematics community. I was dismissed from my research teams. According to an Igbo proverb, quote, "A new fowl in a new land looks at the old fowls to learn how to crow in their new language," unquote. I was dismissed because I was the new fowl in the new land of the massively parallel processing supercomputer. Back on June 20, 1974, I was the new fowl in the new land of the sequential processing supercomputer that solved only one problem at a time. For the 16 years onward of June 20, 1974, and according to an article in the June 20, 1990 issue of the Wall Street Journal, I, Philip Emeagwali, was the new fowl who did not look at the old fowls, or my metaphor for the community of 25,000 supercomputer scientists that were led by Seymour Cray. I did not learn from the old fowls how to crow or program an isolated processor that defined the sequential processing supercomputer and defined the vector processing supercomputer. In my lecture of July 8, 1991 at the International Congress of Mathematicians, the process of massively parallel processing initial boundary value problems arising in calculus and physics, and the process of solving those problems at once was a strange idea that International Congress of Mathematics only holds once every 4 years and was to the mathematician what the Olympic Games is to the athlete. As a research extreme scale computational mathematician My discovery lecture to the research mathematicians at that international congress was on the 9 new partial differential equations of calculus that I invented. Those partial differential equations were in the news and were the cover story of the May 1990 issue of the Siam News that was the most widely read bi-monthly news journal within the global mathematics community. Presenting my mathematical inventions at that international congress gave me the sense of accomplishment that an athlete will have after winning a gold medal at the Olympic Games. I felt like I won gold medals for my contributions to the modern calculus and to the extreme scale algebra that must be formulated to solve the new calculus. I felt like I won gold medals at the Olympic Games of mathematics that holds once every 4 years. I felt like I was inducted into the Mathematics Hall of Fame. Delivering that lecture was more meaningful to me because that International Congress of Mathematicians of July 8, 1991 took place in my adopted hometown of Washington, D.C., where I spent nearly a decade onward of June 8, 1977, doing most of my mathematical research and inventing my 9 new system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern calculus that encoded the second law of motion of physics. Since June 10, 1977, I was a familiar face at the front desk of the U.S. Library of Congress in Washington, D.C. The U.S. Library of Congress is the largest library in the world. Some of my contributions to calculus and algebra occurred while I was reading, researching, and writing inside the U.S. Library of Congress. In the early 1980s, I took the 15-minute walk from my residence at 1915 East-West Highway, apartment 303, Silver Spring, Maryland, to the metro station of Silver Spring, Maryland. From metro station, I took the red line for the 30-minute ride to Union Station that is near the U.S. Capitol Building, Washington, District of Columbia. From Union Station, I took a short walk to the U.S. Library of Congress. I went to the U.S. Library of Congress because in those days it took 3 weeks to complete an interlibrary loan request. Rather than wait for 3 weeks, I went to the U.S. Library of Congress to get instant access to the rarest mathematical materials. In the early 1980s, I was also a familiar face in the one-room library of the Embassy of Nigeria in Washington, D.C. I went to the Embassy of Nigeria to read Nigerian newspapers. I discovered that the Embassy of Nigeria is the place to meet the who's in the Nigerian society. That's where I ran into Mashood Abiola, who strolled into the one-room library, dressed in an off-white suit and carrying a big dark brown leather bag. So I spoke to Mashood Abiola about a decade and a half before he became the presumed president of Nigeria. Solving an initial boundary value problem of modern calculus that's governed by a system of coupled nonlinear time-dependent state-of-the-art partial differential equations, and solving that problem across a new internet that is a new global network of 64 binary thousand tightly coupled processors that were already available in the market is so intellectually demanding that it was dubbed a grand challenge problem. For that reason, I was mentally exhausted by the late afternoons of the late 1970s and early 80s. I rested my brain from doing calculus and calculating across my new internet that is a new global network of 1 binary million bidirectional regular short and equidistant email wires. I rested my brain by playing 3 to 5 sets of tennis games. After 10 years of playing tennis, almost daily, standing out in the sun, and a tough workout regimen, I was ranked by the United States Tennis Association, or the USTA for short, as a level 5 tennis player. I defeated the number 1 seeded tennis player of the Howard University tennis team that I met practicing at the Banneker Recreation Center tennis courts. And I defeated the number 1 seeded tennis player of the University of Wyoming that I met in Casper, Wyoming. And I defeated him with the consistent ground strokes, great agility, marathon level fitness, and speed of a tennis baseliner. I gave up playing tennis in part because I was programming supercomputers 12 hours a day. I also gave up tennis in part because I had few level 5 tennis players that I could play with. Playing against weaker tennis players is good for my confidence and ego, but it does not improve my game. For the same reason, a level 6 tennis player would not want to play with me. On 3 occasions, I played against retired level 7 tennis players, the tennis players you watch on television. These world-class tennis players are overpowering with their 100 miles per hour serve and volleys. I discovered that I recuperated faster when I played tennis in the late afternoon, and that I recuperated slower when I did not play tennis, but instead watched television in the evening. In the late 1970s, I recuperated with 3 to 5 sets of tennis games at the Banneker Recreation Center tennis courts that was named after Benjamin Banneker and that was across the street from and between the School of Engineering of Howard University and the Benjamin Banneker High School, Washington, D.C. Benjamin Banneker was the prominent black American mathematician of Senegalese ancestry. Benjamin Banneker was extolled as a scientific genius by both Thomas Jefferson and the French Academy of Sciences. Benjamin Banneker was on a U.S. postage stamp and is the subject of school reports. Benjamin Banneker famously and politely challenged Thomas Jefferson by famously writing that, quote, "The color of the skin is in no way connected with strength of the mind or intellectual powers," unquote. In the summer of 1977, I was 22 years old and hanging around Charles Drew Dormitory of Howard University, Washington, D.C., and doing so without realizing that I will cross paths with Charles Drew in school curricula and reports. Charles Drew is best known for his contributions to the blood bank. I played tennis at Banneker Recreation Center tennis courts that was at Euclid and 9th Street Northwest. I played tennis at Banneker courts during the 2.5 years onward of October 1978 that I lived at the corner of Euclid and 16th Street Northwest in the Adams-Morgan neighborhood of Washington, D.C. I also went to 16th and Kennedy Streets Northwest to play tennis at the Rock Creek Park Tennis Center. That tennis center is to Washington, D.C. what Wimbledon lawn tennis is to London, England. As a computational fluid dynamicist, I understand the motions of tennis balls in a deeper way that my tennis partner cannot understand. I understand that the top spin of first serves are spinning at 1,000 revolutions per minute. Wilfred St. John, who was born in the Caribbean, and Ron, who was born in Trinidad, were my two favorite tennis players of the early 1980s. We played at the 4 tennis courts of Rosemary Hills neighborhood of Silver Spring, Maryland. The tennis courts were at 2450 Littensville Road, Silver Spring, Maryland. Those tennis courts are adjacent to the newer Gwendolyn Cofield Community Recreation Center and to the Rosemary Hills Littensville Local Park in Silver Spring, Maryland. Those 4 tennis courts were a short walk from my residence at 1915 East-West Highway, Silver Spring, Maryland. Ron, who was in his mid-20s, was very strong, very tall, and very fast. But Ron gives away his hard-won points by making too many mistakes. Ron had a first serve that terrified other tennis players. Ron serves his tennis balls flat and serves them with 0 topspin and serves balls at 120 miles per hour. Ron's first serves leave their imprints on the hard court. Ron serves at the same first serve speed that Arthur Ashe served in Wimbledon, England. The only way I could return Ron's first serves was to stand several feet outside the tennis court to receive them. I used the number of revolutions per minute and the speed of the tennis ball to model the motion of the tennis ball and to do so from a system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern calculus that originates from my blackboard and that I must solve as 64 binary 1,000 computer codes that were running simultaneously and executing across a new internet. That is a new global network of as many tightly coupled processors that shared nothing with each other. I had to be physically fit to be intellectually fit. In the early 1980s, my 3-hour jogging trail was through the Rock Creek Park of Washington, D.C. I began jogging through the Rock Creek forest at 7 a.m. and I jogged for 3 hours. Sometimes I jogged through the city. For my city runs, I started from Metro Station of Silver Spring, Maryland, and jogged along Georgia Avenue towards downtown Washington, D.C., making a right turn at Howard University and heading towards George Washington University and back to Silver Spring, Maryland. It is impossible for me to get lost in Washington, D.C., just as it is impossible for a cat to get lost in its neighborhood alleys. For this reason, I was at home, both physically and intellectually, whenever I am in Washington, D.C. I was at home during the 1991 International Congress of Mathematics that took place in my backyard of Washington, D.C. and took place a jogging distance from my former residence in Silver Spring, Maryland. It seems surreal and a strange coincidence that I followed the footsteps of Benjamin Banneker, even though he was born 2 centuries, 2 decades, and 3 years before I was born. Benjamin Banneker was born in colonial America, and I was born in colonial Africa. I was born on August 23, 1954 in Akure, in the British West African colony of Nigeria. The father of Benjamin Banneker has his ancestral roots in present-day Senegal, West Africa, and we both were first-generation Americans. I was a regular visitor to the Benjamin Banneker Museum in Ellicott City, Maryland, and a regular hiker along nearby trails. Like Benjamin Banneker, I was publicly extolled by a U.S. president who acknowledged my contributions to scientific knowledge. Like Benjamin Banneker, I am on postage stamps. Like Benjamin Banneker, I am the subject of school reports for my contributions to the development of the computer. I am the research computational mathematician who searched for new calculus and new algebra that are most suitable for the most massively parallel processing supercomputer in the world. I searched for new mathematics, and I searched for the 20 years onward of June 1970. After 20 years, I was at the frontier of knowledge of new calculus and new algebra. Only a few hundred of the 10,000 research mathematicians that read the cover story of the May 1990 issue of the Siam News could understand my contributions to calculus and to algebra. But those research mathematicians that were at the frontiers of knowledge of modern calculus, extreme scale algebra, and computational physics, and that attended my lecture on July 8, 1991 at the International Congress of Mathematicians, understood my contributions to the partial differential equations of modern calculus. Those research mathematicians also understood my contributions to large-scale algebra that arose from solving those partial differential equations. Briefly, I explained to the International Congress of Mathematicians the new calculus and the new algebra that I contributed as never before seen mathematical knowledge. I explained at the International Congress how I mathematically invented the 36 partial derivative terms that I contributed to the calculus of extreme scale computational physics that is used to recover otherwise unrecoverable crude oil and natural gas that were buried a mile deep in the Niger Delta oil fields of southeastern Nigeria. In the early 1980s, and while I was living in the Washington, D.C. metropolitan area, I made two contributions to modern calculus. My contributions were new, and for that reason were not in any calculus textbook of the 1980s and earlier. My first contribution to mathematics was in the early 1980s. That mathematical contribution was my theoretical discovery of 36 formulas, each called a partial derivative term of calculus. I mathematically discovered that my 36 formulas made my 9 partial differential equations of modern calculus that I invented to more accurately represent the motions of crude oil, injected water, and natural gas that were encoded in the petroleum reservoir simulator. My new partial differential equations are more accurate when used to recover otherwise unrecoverable crude oil and natural gas. My second contribution to modern calculus occurred from the mathematical studies and laboratory experiments that I conducted in the mid-1980s. That contribution to extreme scale computational mathematics was my invention that the technology of massively parallel processing makes the computer faster and makes the supercomputer fastest, and my invention of how those unheard of supercomputer speeds and how to harness millions upon millions of processors and harness them to solve the toughest problems arising in modern calculus, large-scale algebra, and extreme-scale computational physics. Such grand challenge problems of supercomputing include the general circulation model that must be used to foresee otherwise unforeseeable climate changes. I invented how to harness the processors within the modern supercomputer, and I invented how to harness the fastest computation, how to use the fastest computation of a supercomputer to more accurately solve what mathematicians describe as initial boundary value problems of modern calculus. My most important contribution to calculus was my invention of how to solve the toughest problems arising in calculus and how to solve them across motherboards or across an ensemble of 65,536 cooperating processors that shared nothing with each other. In 1989, it made the news headlines that I invented how to solve the toughest problems arising in modern calculus, large-scale algebraic computations, and extreme-scale computational physics, and that I invented how to solve those initial boundary value problems and how to solve them across a new internet, that is a new global network of 64 binary 1,000 tightly coupled processors that were already available in the market. I invented how to solve those tough problems and solve them across an analogous global network of 64 binary 1,000 computers. My invention of how to parallel process across a new internet was a paradigm shift that changed the way we solve the toughest problems arising in modern calculus and extreme scale algebra. In the old way, the toughest problems in modern calculus, extreme scale algebra, and extreme scale computational physics were unsolvable or impossible to compute on the blackboard, or were inaccurately solved or computed on one motherboard or on one computer that is powered by only one isolated processor that was not a member of an ensemble of processors that communicates and computes together and as one seamless, cohesive supercomputer. That invention was the reason my mathematical contribution to modern calculus, extreme scale algebra, and extreme scale computational physics was front page news in the world of mathematics. I provided the lockdown evidence when I invented how the toughest problems arising in modern calculus, extreme scale algebra, and computational physics can be solved on the blackboard, can be solved beyond the motherboard, and can be solved across a new internet that is a new supercomputer and that is a new computer. I invented that new internet as a new global network of 2 raised to power 16 processors that were already available in the market and that were married together as one seamless, cohesive whole unit, and married together by another global network of 16 times 2 raised to power 16 regular and short email wires that were equal distances apart. I mathematically visualized that new internet as uniformly encircling a globe that is mathematically embedded within a 16-dimensional hyperspace. I invented how to push the frontier of modern calculus and extreme scale algebra, and how to do so to solve one of the most computation-intensive problems arising in extreme scale computational physics, and that is called petroleum reservoir simulation. The Niger Delta oil field doesn't fit into a lab or into one computer. For that reason, I invented how to fit the Niger Delta oil field into a new supercomputer that is not a computer per se, but that is a new internet de facto. My new internet is powered by an ensemble of 65,536 commonly available processors, with each processor operating its own operating system and with each processor having its own dedicated memory that shared nothing with each other. I invented how to solve one of the most computation-intensive problems arising in supercomputing, and how to do so by mathematically inventing how to compress the infinite times to solution to finite times to solution, and finally by inventing how to compress 65,536 days or 180 years of time to solution to just 1 day of time to solution. It takes infinite calculations and infinite time to solution for even the fastest supercomputer to solve the toughest problems arising in modern calculus, extreme scale algebra, and computational physics. It takes infinite calculations and infinite time to solution to solve those problems directly and exactly. As a matter of fact, or by definition, the fastest supercomputer only solves calculus problems indirectly and approximately, and only solves the algebraic restatement of that calculus problem. That error, in part, explains why tomorrow's weather forecast is not an exact science. I can say more if I have your permission to use a few mathematical shorthands that are only understood by the few grand wizards of calculus that were initiated into the priesthood of mathematics. Please allow me to quote myself and to quote from my July 8, 1991 lecture that I delivered to research mathematicians that were attending the International Congress of Mathematics. This was what I told those research computational mathematicians that were at the frontier of mathematical knowledge. Quote, to parallel process or to process many problems or processes at once instead of processing only one problem at a time is the necessary condition for solving the diagonalized system of equations of algebra that I invented from my explicit finite difference discretizations of my governing system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations that defined my initial boundary value problems of calculus that was at the mathematical foundation of extreme-scale petroleum reservoir simulation. In particular, I continued, a sufficient condition for accurately solving the initial boundary value problem is to attain infinite speedup. I invented how to use a new internet that I invented and how to use that new internet to compute 65,536 times faster than one computer that is powered by only one isolated processor. And with that one computer computing alone, to solve one extreme scale problem arising in computational physics, in which the laws of physics were central to the definition of that computation-intensive problem, unquote. I was the inventor that saw 9 unseen partial differential equations of modern calculus. I saw a 65,536-fold increase in high-performance supercomputer speed for executing the fastest floating point arithmetical operations. The potential to achieve that speed up pre-existed within my new internet that I visualized and programmed as a new global network of 65,536 processors, with each processor operating its own operating system and with each processor having its own dedicated memory that shared nothing with each other that were already available in the market, or a new global network of as many computers. That new internet was a new frontier in extreme scale computational mathematics that I had to cross to see a previously unseen massively parallel processing supercomputer that is the modern supercomputer that is used to conquer tomorrow's challenges, such as solving the toughest problems arising in modern calculus and in extreme scale algebra. I'm Philip Emeagwali. In 1989, I was in major US newspapers, such as the June 20, 1990 issue of the Wall Street Journal. I was in the news because I invented the lockdown evidence of how to compress 65,536 days or 108 years of time to solution on one computer to only 1 day of time to solution across a new internet that is a new global network of 65,536 computers. I invented how to execute the excruciatingly detailed petroleum reservoir simulation, and I invented how to solve that initial boundary value problem of modern calculus and computational physics, and I invented how to solve that problem as soon as possible. For that massively parallel processing supercomputer accomplishment, I won the top accolades from the top technical societies in the United States. As a technological inventor, I created something, namely a new internet that is a new supercomputer that could have been created but was not created. By seeing something where nothing existed, the discoverers and inventors made darkness visible. My invention was how to make a new internet that is a new global network of 65,536 tightly coupled commodity processors, and how to make those cooperating processors invincible individually and yet visible as one seamless, cohesive supercomputer that solves extreme scale problems in algebra. That was how I crossed the frontiers of knowledge to see a new internet that was previously unseen. Throughout history, every inventor entered the unknown world or the terra incognita of knowledge before the invention became the news headlines. Their biographers or authorized storytellers came on the scene often decades after the discoverer is no longer with us. The fastest supercomputer in the world occupies the space of a soccer field and requires building a new multi-story facility to house the millions upon millions of commodity processors that will enable it to execute the fastest computations. Extreme scale algebra is the recurring decimal in extreme scale computational physics that in turn is the recurring decimal within the millions upon millions of commodity processors that make the new supercomputer super. Executing extreme scale computational physics codes demands unreasonably large execution times. I made headlines in major US newspapers because I invented how to reduce 180 years of time to solution across one computer powered by only one processor that was not a member of an ensemble of processors to just 1 day of time to solution on the massively parallel processing supercomputer that is a new internet, that is a new global network of 65,536 processors. That invention was recorded in the June 20, 1990 issue of the Wall Street Journal. That invention of a new internet, that is a new computer, is my signature invention. That invention is my contribution to calculus, algebra, and computer science. That invention is the reason the 12-year-old American is writing school report on the contributions of Philip Emeagwali to the development of the modern computer. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you very much.
Insightful and brilliant lecture.
Thank you.
Insightful and brilliant lecture.